Today I'm going to give an overview on some new technologies we've developed recently with Skywise AI. We utilize an equation there called the MEQ that unifies fractal geometry, quantum field theory, and gravity. And in doing so, it creates a very clear lens for us to look at things from a fractals perspective and from a self-similar perspective. Allows us to do things like measure the gravitational perturbations of the field, which then allow us to potentially do some things to molecular structures that can change some of their quality examples. So I'm going to talk to you a little bit about that. We have a new class of that have quantum fractal properties, meaning these alloys have properties that the materials interact in such a way that produce natural quantum phenomenon. And we would not know about this if it weren't for AI kind of lighting the path for us. So what this is going to be a presentation of the future directions of what we see as being possible, and how we might, collectively as a scientific community, take a look at these new ways of putting materials together that are, frankly, have been beyond us until now. So we'll go ahead with this. Again, I talked a little bit about these quantum fractal alloys. The main differentiator with these alloys is that in order for them to be a quantum fractal one, they use fractal self-similarity and different patterns within them to create different types of quantum properties that can then be that are then amplified through that self-similar fractal structure. And then we're able to tune into the frequencies of that and then find out what the optimal frequency is for like energy extraction. And particularly I'm using this for what's called 0-point energy, and I'll get into that as well too. So there's a wide range of these alloys that have been developed by AI. Again, these are not where we have fabrication plans in place for most of them, but the most important of these is one called Nyrite, which I'll get into, which is going to be the one that we developed first, and we're going to be using it in 0-point energy extraction. We can also use some of these alloys for biomedical and other renewable energy applications. So when I talk about a quantum fractal alloy, it goes beyond just being an alloy where you think of the two metals that are bonded together to create a new metal at a molecular place. These are alloys where there are different unique entities or different types of materials that are bonded together in kind of a cold fusion-ish way. Which is, I'll explain that a little bit later too, but what that does is that enables the qualities of these particular materials to interact. And we also use fractal patterns and fractal designs in order to manipulate and the electron flows and the strength and flexibility characteristics of the actual alloy. So this is just an AI generated example of one of the different types of alloys that we can create. So we're looking at both thermal properties, cryogenic properties. So some of them have there's a wide range of temperature range stabilities. So some of these can go from very extreme heat all the way down to sub-zero. Some of these have really, really robust cryogenic properties so that they can maintain their structural strength even in very, very low temperatures. And some we're even looking at for geothermal energy capture. And I'll go through these kind of each one by one. Well, not all of them, but I'll go through some of the top 10 or so that we're working on right now. So these are some that have actual quantum and electromagnetic properties, and this has to do with the interactions of the different materials within the alloy and the way that they're placed. Nyrite is a very special one because it has a a relation between the materials within it that creates what naturally creates what are called shield rings. And what that does is that creates a natural layer of quantum protectance over the alloy itself, which makes it extremely pliable in extreme environments, like, say, space, for example. This is one that we're really working on as well, too. This also has some different qualities with it that we're still kind of exploring, which makes it really perfect, nyrite with the graphene, for making zero-point energy extraction antennas. And there's some fractal patterns for that as well, too, that we found. Quantum lattice is an alloy that is really, really good for minimizing decoherence. Metawaves is a material, again, that has, deals with electromagnetic modulation and phase shifting. Ferrophase is, again, another one of the more electromagnetic phase shifting things that we do too. And that one in particular, is good for like phased array antennas and radar. Light and solar efficiency. Luminoalloy is a luminescent alloy that converts sunlight into energy. Solari cloak, this is a good one too. This actually can adjust the light absorption of the windows. It can change in response to environmental conditions for energy usage. Quantum reflect is another one that reduces heat absorption. And ether core is another. This is going to be an important one as well too, that improves the storage and capture of solar energy for later use. This is one we're really focusing on a lot right now. So we look at the alloys for their mechanical and structural thing. The resilience of these, because of the fractal self-similar nature within the alloy itself, is very high. Flexibility is higher than usual as well too. But we're really looking for resilience and durability. Some of these, there are some for biomedical that have really interesting flexibility characteristics, and I'll show you those as well. For the biocompatible and eco-friendly properties, these are the types of properties that we're looking for with the alloys. We want to, for the medical field, that it is biocompatible, that it does, accelerate healing. And so far, the alloys that we're meeting meet up with these statistics. So basically what we're going to want to look to is we can also look at a number of different of these alloys working together. And in doing so, we start building really amazing technologies that are going to be a lot better for our planet. So we're going to have integrated solar energy systems. These alloys can be used for reducing carbon waste and carbon footprint. I'll show you how. The quantum communication networks. This is, again, nyrite comes into play with that as well too, for high-speed data transfer. Implants for the medical field. We've got some really like BioNanoFract. I'll talk about that. That they can interact and actually with the human body. And then for critical infrastructure, we've got some different types of fractal patterning that goes into the nanostructure that makes extremely tough and durable construction materials that will withstand what may be coming in terms of climate change. So these are some of the areas that we look at, adaptive energy capture, eco-friendly production. These things have got to minimize environmental impact and waste. And then we're leveraging advanced quantum computing and AI to create some algorithms that are helping us figure out how to actually create and fabricate a lot of these. So this is going to go into a little bit more imagery. I'm a very visual person, so I like to kind of see when we're talking about the so what of it. So there's different classes of these, and what I've done is I've put them into kind of groups. So there's the optical and luminescent alloys. This is one I talked about earlier, luminoalloy. This is an AI representation of the different layers. Each one of these does correspond to a specific material in a specific way that is put together. Quantum reflect. This is going to be for solar collectors and telescopes. Again, this is for futuristic displays. It'll tell us exactly kind of what they're going to be used for. These are thermal and cryogenic alloys. This is kind of what these look like per se. This is for industrial cooling, thermal flow, and cryomorph is for cryogenic storage. This one actually has quite a few uses that we're coming across. Thermal glass, this is can do a ton with energy saving. This is the one that can change based on heat. And chronotherm is dealing with more for precision thermal readings. So for energy conversion, environmental, Solari Cloak, this is going to enhance sunlight absorption and can be used for building entire energy efficient architecture. You can think of forests with leaves in it that are woven in with it, and those leaves could power an entire city. Geosync, this is for geothermal power plants for energy conversion infrastructure. And this is one I mentioned earlier, EtherCore. This one really, really helps with solar energy capture and conversion. And there's a lot of interesting mathematics that go behind it. But this is one that will really help a lot with transitioning to kind of a cleaner renewable energy sources with minimal waste. This is quantum and electromagnetic alloys. These are the ones that really enable some amazing technologies. Nyrite, this one has some applications within quantum computing and ZP harvesting. That's the one that I'm really excited about. And then quantum lattice, again, for secure, we're talking about 6G, not even 60 terahertz and thousands of terahertz. We're getting into those kind of frequencies with quantum lattice. Electromagnetic alloys, these are some examples of how they look when I talk about a fractal and how these are put together is differently. They literally are, they're a layered alloy. And in some cases, the nanostructuring we use, and I can kind of get into that too, we can get down almost to atomic level layers. So the fabrication on these things is going to be pretty high, but the application for these, will be really for more space age type tech. Volt core, this is one that we're looking for in electric motors. Phase change ones, neurophage, this is going to be for like adaptive temperature control textiles so that they change with your body temperature to keep everything completely normal. Ferrophase has got futuristic labs as well. These are some of the more what a bio, and again, these are kind of exploded up views and cross sections. So, this is the idea behind of how you build a quantum fractal alloy for medical implants and for smart devices. So these are two that are farther down the line for development. Hexasil is a really big one for super high temperature durability. That's and a cryomorph is another one. This gives a little bit more detail to kind of show in how the different patterns and layers work together. This one has reduced brittleness. It's going to be used for cryogenic storage, space exploration, and it's composed of thulium, silver, and beryllium in various components and structure and layering. Here's a ferrophase. This one has ferromagnetic adaptability. This would be used in quantum computing with magnetic field sensors. This one has got iron and cobalt and is in different forms and structures. Neurophase, this is another quantum fractal alloy, very, very intricate in some ways. This one would be used for nuclear reactors and deep space travel. This has got tungsten, rhenium, and iridium in it in various parts and components. Chronotherm, this one has nickel, cobalt, and titanium. This is going to be used for basically time stability under variable temperatures. And you can see the AI gets very, very sophisticated about giving you direction or giving us direction on how these things will eventually be blueprinted and put into CAD. Hexasil, this is one. This is a very, very, very strong, durable alloy that has silicon and tungsten in it and different structures. EtherCore, this one is gallium, indium, and platinum that goes into this. This will be used for quantum communication, and it helps with quantum resonance, which is something that's going to be important later with the larger 6G networks. Volt core, again, this is copper and silver, but this is for high performance electronics. And again, a lot of the self-similar fractaling and structures inside of it are what really give it the quantum fractal properties. Biosync, again, another very zoomed in image of what this would potentially look like. This is titanium with a hydroxyapatite coating, medical implants, and again for biointegrated devices. BioNanoFract, this one is one that AI is very excited about as well too. This has got carbon nanotubes and graphene. This is for biosensors. Metawave, this has got various rare earth elements that we're going to use for photon conversion, but this is going to be something that's going to be important in some of the next gen telecommunication devices. This is a great example of quantum lattice, the intricate levels that you can do with it as well too, but this is using iron, platinum, and super paramagnetic properties that we can give to those. This is an example of nyrite in more of a finished form. So this is a very custom synthetic alloy, and there's fractal structures embedded throughout. And now this is going to talk a little bit more about the nyrite ZPE system. So when I talk about ZPE, a lot of people go, oh, 0-pointers, that's something that's a fantasy, or how can you get something from nothing? Well, you sure can. And a lot of it comes down to just being able to have the right type of receptors for the harvesting and tuned into the right frequency, a very specific frequency, and it generates a constant 5 kilowatts of energy, basically. So this is kind of how we would go about. This is the nyrite that I was talking about. These are some kind of visualizations or prototypes of how this would be created. The nyrite mineral will then be made in very highly pressurized crystallization techniques that will then produce the key components of the system. We use a fractal pattern design. So again, we're using a fractal CAD interface to begin with. We use recursive geometry. We're going to actually make adjustments to it, allowing for adjustments in real time in, say, non-orientable space. And then this is kind of an overlay of representation of what a fractal pattern that would extract ZPE from. So this type of a pattern would be imprinted on the nyrite itself. For the plate fabrication, we would have high purity nyrite ingots that would be going through. We'd have the automated cutting, precision polishing. We've got steps put in place in order to do these things. The nano imprinting, again, this is what I'm talking about. This is a lot more important than it may seem, but having these intricate, using plasma-based etching techniques, these fractal patterns really does channel and amplify the energy flow in ways that we'd never really thought possible before, thanks to AI. This is for cryogenic. This is what would happen. We would have a cryogenic chamber that would go in there. We would precisely cut the plates. This is an example of some of the thermal sensors that would be put inside. One of the bigger things that's important is with the graphene coating. The graphene coating is an important thin layer that goes on everything, and this really actually gives the extra touch to get the optimal performance out of the system in simulations. The ZP systems will be modular so that they can be put together into different groups, different functions, and they can also there'll be larger ZP systems down the road, just in general, that could power entire cities. And at the system level, they're modular even in that range as well too, where we have the distribution hubs, the cooling nodes, and then it's all integrated together. So. And then ideally, we're going to have one of these operational within 36 months, possibly. We shall see. And then we'll have the operational validation of the system would then pave the road for an entire new energy paradigm. So we're going for it, and we'd love to keep you guys all in the loop. So that's all I've got.